Okay, so we're always hearing about AI, transforming like the digital world, right?
Yeah.
But the buzz around robots
Yeah.
actually like doing stuff, in the physical world,
Totally.
it's getting so much louder these days.
Yeah. Yeah.
And for good reason.
For good reason.
Because we're looking at some pretty stark predictions.
Mm-hmm.
Like we're going to be short around 50 million human workers by the end of the decade.
Wow.
50 million.
Yeah.
That's a big number.
It is a huge number.
So I think it really underscores the urgency and potential of advancements in robotics.
It does when you consider the scale of global operations
Right.
and the increasing demand across various sectors, like that kind of shortfall has significant implications.
Yeah,
It pushes us to find intelligent and adaptable solutions in automation.
absolutely. And that brings us to what we're diving into today.
Right.
You've been curious about the latest, advancements in robotics.
Mm.
And recently, NVIDIA made some really fascinating announcements,
Yeah.
particularly around their Isaac GR00T N1 robot
Okay.
and the underlying technologies.
Right.
So our mission today is to kind of unpack these announcements,
Got it.
go beyond the initial news, and
Right.
really try to understand why this matters for the future of AI and robotics.
Okay.
I think there are some genuinely surprising aspects to all this
Yeah.
that could fundamentally shift how we think about building intelligent machines.
Absolutely. It's not just about building a cool-looking robot.
Right.
These advancements tackle some fundamental challenges that have long been roadblocks in the field of embodied AI.
That's right. From what we've gathered, there are 3 core challenges that NVIDIA is directly addressing: the data problem,
Right.
figuring out the right model architecture for these robots, and then the big one, how do you actually scale this up?
Right.
So it's not just a lab experiment.
Yeah, that's a big one.
Okay, so let's unpack this.
Yeah.
Starting with the data problem. Training robots to perform a wide range of tasks
Right.
in diverse environments requires a massive amount of data.
Yeah.
But unlike the readily available text data
Right.
that we have for large language models, LLMs,
Right.
the physical world presents a far more complex
Yeah.
and sparse data landscape.
Yeah.
So NVIDIA's approach here is really interesting because they're directly tackling this inherent limitation.
Right.
Where does all that data come from
Yeah.
in the real world for robots?
Right.
It's not like training a language model on the internet.
That's precisely the bottleneck.
Right.
Real-world data collection for robot training can be incredibly time-consuming,
Yeah.
expensive,
Right.
and sometimes even dangerous.
Yeah.
Think about a robot learning to navigate a chaotic warehouse or perform delicate assembly tasks. Gathering enough diverse examples of successful
Right.
and unsuccessful attempts in every conceivable scenario is a monumental undertaking.
Yeah. It's a lot.
It's a significant barrier to progress.
And this is where NVIDIA Omniverse comes into play.
Okay.
They're calling it the operating system for physical AI.
Interesting.
It sounds pretty grand.
Yeah.
But what does that actually mean for solving this data problem?
Yeah.
Is it just a fancy way of saying they have better data sets?
The real insight here is that Omniverse allows developers to generate massive amounts of synthetic data.
Okay.
It's essentially creating virtual worlds and populating them with realistic environments, objects, and even simulated robot interactions.
Yeah.
This fundamentally bypasses the biggest bottleneck in robotics training,
Yeah.
potentially accelerating development by orders of magnitude
Wow.
and democratizing access for researchers who lack vast real-world data sets.
Okay, so instead of painstakingly recording real-world robot actions,
Right.
developers can essentially build these digital playgrounds for the robots to learn in.
Right.
How does that process work exactly?
Yeah.
It can't be as simple as just creating a video game.
The process involves developers taking the real-world sensor data or demonstrations they might already have
Okay,
and feeding that into Omniverse.
got it.
Then they use Omniverse to condition something called Cosmos.
Cosmo.
Think of Cosmos as a generative model that can then multiply that original data into incredibly diverse,
Okay.
yet photorealistic data sets.
Yeah.
They're talking about creating systematically infinite controlled data.
Systematically infinite. That's a big claim.
Yeah.
So they can essentially take a few real-world examples
Right.
and then have this Cosmos system churn out countless variations.
Yeah.
Covering different lighting conditions, object placements, and even unexpected events.
That's right.
what are the practical limitations of
Mhm.
creating truly infinite variations?
Right.
Are there computational constraints
Yeah.
or risks of generating irrelevant data?
That's a crucial question.
Right.
While systematically infinite highlights the potential scale,
Right.
there are indeed practical considerations. Computational resources are a factor, of course,
Yeah.
but the key is in the controlled aspect.
Okay.
Developers can define the parameters
Mm-hmm.
and variations they want to explore,
Right.
ensuring the generated data remains relevant to the tasks the robot needs to learn.
Yeah.
It's about smart multiplication rather than random generation.
That makes a lot of sense.
Yeah.
So they're essentially bootstrapping the training process
Yeah.
with this synthetic data.
Right.
And then what happens with all this generated information?
Right.
Does the robot just learn in this virtual world
Mm-hmm.
and hope for the best when it encounters the real one?
That's where Isaac Lab comes in.
Isaac Lab.
Developers use Isaac Lab to further refine the robot's abilities.
Okay.
After the initial training with the synthetic data,
Got it.
they can use techniques like imitation learning,
Okay.
where the robot learns by trying to mimic the actions demonstrated in the augmented data,
Mm-hmm.
or reinforcement learning,
Right.
where the robot learns through trial and error, with AI feedback within these controlled virtual environments.
So the synthetic data gets the robot to a certain foundational level
Right.
of understanding and capability.
Yeah.
And then Isaac Lab helps it fine-tune its skills and adapt to more nuanced situations.
That's right.
Okay, now once these robot policies,
Right.
the AI that controls the robot are trained,
Okay.
how do they actually test them
Right.
before unleashing them into the real world?
Yeah.
You can't just hope for the best, right?
Yeah.
That sounds like a recipe for disaster in a warehouse.
Precisely.
Right,
Field testing in the real world can be risky and costly.
right.
So NVIDIA is leveraging Omniverse again
Okay,
for rigorous testing in virtual environments.
okay.
They use it for both software in the loop
Right.
and hardware in the loop testing.
Oh, can you explain that a bit more?
Okay.
What's the difference there and why should we care?
Software in the loop essentially means that the entire robot system,
Okay.
including its control software,
Mm-hmm.
is simulated.
Right.
Hardware in the loop involves using the actual robot hardware
Okay,
connected to the simulated environment,
got it.
allowing for testing with real-world dynamics, sensor feedback, and even the effects of physics.
Okay.
This is crucial because it introduces the complexities of real-world sensor noise, motor inaccuracies, and physical interactions
Right.
that a purely software simulation might miss,
Right.
leading to more robustly trained robots.
So it's like the robot's brain.
Exactly.
The software is being tested in a digital body.
Yes.
And then the actual robot body is plugged into that same digital world to see how it behaves.
Exactly. This digital twin incorporates real-world physics,
Okay.
allows for domain randomization.
Domain
This
randomization.
involves varying aspects of the simulation, like lighting, textures, and even the physical properties of objects,
Okay.
to force the robot to learn generalizable skills,
Hmm.
rather than overfitting to a specific virtual environment,
Right.
and provides high-fidelity sensor simulation. So the robot's virtual eyes and feelers behave as they would in reality.
That sounds incredibly detailed.
It is.
And how do they scale up the testing to see how multiple robots would work together?
Yeah.
Because in many real-world scenarios, it's not just one robot operating in isolation.
This is where Mega comes in.
Yeah.
Built on the Omniverse blueprint,
Okay.
Mega allows developers to test fleets of these trained robot policies at scale.
Okay.
They can simulate entire environments, like a virtual factory floor,
Yeah.
and see how multiple robots interact and coordinate to perform tasks.
They even gave an example of Foxconn testing heterogeneous robots
Right.
in a virtual NVIDIA Blackwell production facility.
Yeah.
That's pretty concrete.
Yeah.
So Mega isn't just about individual robot performance.
Right.
It's about testing their ability to collaborate on things like spatial reasoning, navigation movement, and even complex manipulation tasks.
That's right.
It's about testing the whole system.
What's fascinating here is the ability to test the entire system.
Right.
The individual robots and their interactions
Yeah.
in a controlled virtual environment before any physical deployment.
Right.
It significantly reduces the risks and costs associated with real-world testing
Yeah.
and allows for rapid iteration and refinement of robot behaviors.
Okay, so with this powerful ability
Right.
to generate training data
Mm-hmm.
and establish robust testing methods,
Yeah.
let's now turn our attention to the core intelligence powering these robots,
Right.
the NVIDIA Isaac GR00T N1.
Okay.
So they're tackling the data problem with synthetic data
Right.
in Omniverse and Cosmos,
Right.
and they're rigorously testing
Yeah.
in these virtual environments with Omniverse and Mega.
Right.
Now let's get to the star of the show.
Okay.
The NVIDIA Isaac GR00T N1.
Got it.
It's described as a generalist foundation model for
Right.
humanoid robots.
Got it.
I think that sounds like a big leap
It is.
because the term foundation model,
Right.
much like the large language models, LLMs that power chatbots,
Right.
implies a model trained on a vast amount of data
Yeah.
that can then be adapted or fine-tuned
Mm-hmm.
for a wide variety of specific tasks.
Right.
GR0T N1 aims to be that foundational intelligence for humanoid robots.
It does. And the generalist part suggests it's not designed for just one specific job, right?
Yeah.
Unlike robots traditionally built for highly specialized tasks
Right.
in, say, an automotive factory,
Yeah,
GR00T N1 is envisioned as being much more versatile.
precisely.
Yeah.
The goal is to create a robot that can learn and perform a multitude of tasks,
Mhm.
much like a human can.
Right.
And the architecture they've implemented is quite interesting.
Okay.
They've opted for a dual system architecture inspired by how humans think.
Okay.
A slow thinking system and a fast thinking system.
Okay.
It's not just a technical detail.
Yeah.
It represents a fundamental shift towards creating robots with more human-like cognitive abilities,
You're right.
allowing them to reason and react in complex situations, rather than just following pre-programmed paths.
Mm-hmm.
So this could unlock a new level of autonomy and adaptability.
Okay. Break that down for us.
Okay.
What does each system handle?
Okay.
What's the benefit of this dual approach?
The slow thinking system
Okay.
is responsible for higher-level cognitive functions,
Okay.
like perception, reasoning, and planning.
Got it.
It's where the robot analyzes its environment,
Mhm.
understands instructions,
Right.
and figures out the best course of action.
Okay.
The fast-thinking system, on the other hand,
Right.
takes those plans and translates them into the precise and continuous motor commands
Okay.
needed to execute those actions in the physical world.
Got it.
Think of it like the difference between deciding to pick up a cup
Right.
and then actually coordinating all the muscles in your arm and hand to do it smoothly.
So one's the strategist and the other's the executor.
Right.
That sounds like a really efficient way to process complex tasks.
Yeah.
And what kind of capabilities does this architecture give GR00T N1? What can it actually do?
They're highlighting its generalization capabilities.
Okay.
It can manipulate common objects with a degree of ease
Okay.
and perform multi-step sequences collaboratively.
Okay.
Think about a robot not just grabbing an object,
Right.
but understanding how to hand it to another robot
Right.
or use it as part of a larger assembly process.
Right.
It's about understanding the context of the action.
That's a significant step up from robots
Right.
that are typically programmed for very specific,
Yeah.
repetitive tasks.
Right.
And the fact that humanoid robot developers can post-train GR00T N1 across different robot designs, tasks, and environments
Right.
using NVIDIA's computing systems
Right.
seems crucial for its widespread adoption.
Yeah.
It's not tied to just one type of robot.
Right.
This adaptability is key to realizing the vision of general-purpose robots
Yeah.
that can be deployed across various industries and applications.
Now, another key piece of the puzzle here seems to be addressing the scaling issue.
Okay.
We touched on data and model architecture.
Yeah.
But how do they ensure these robots can learn and improve efficiently at scale?
Right.
They mentioned something about verifiable rewards like physics.
Right?
That sounds a bit abstract.
This is a really insightful point.
Yeah.
Just like reinforcement learning in language models
Mm-hmm.
relies on feedback to guide the learning process.
Right.
In robotics, verifiable rewards are essential for scaling AI.
Yeah.
And what's more verifiable and consistent than the laws of physics?
Right.
Gravity, friction, how objects interact.
Yeah.
These are fundamental truths that a robot can consistently learn from through simulation.
Right. So instead of a human constantly telling a robot, good job, or try again,
Right.
the physics engine provides inherent feedback.
Exactly.
And this leads us to Newton.
Okay.
Their new physics engine developed in partnership with DeepMind,
Wow.
Disney Research,
Yeah.
and NVIDIA itself.
That's quite a collaboration.
That's a pretty impressive group.
It is.
What makes this physics engine so special for robotics?
Newton is specifically designed
Okay.
with the unique needs of robotics in mind.
Okay.
It's built for handling fine-grained, rigid, and soft bodies,
Okay.
which is crucial for tasks involving delicate manipulation and interaction with deformable objects.
Right.
Think about a robot needing to grasp a fragile item
Yeah.
or manipulate cables.
Right.
Newton should provide the accurate physics simulation
Okay.
needed for realistic training of those skills.
So it's not just about things moving accurately.
Right.
It's about capturing the nuances of how different materials behave.
Precisely. Furthermore, Newton is designed to facilitate the training of tactile feedback
Okay.
and fine motor skills.
Yeah.
This is essential for robots
Yeah.
to develop a nuanced understanding
Right.
of how they're interacting with the physical world through touch.
Yeah.
It's about feeling and responding to those physical interactions in a realistic way.
And I remember them emphasizing that Newton is GPU accelerated,
Right.
allowing for super real-time simulation.
That's right.
Why is that so important for training?
Right.
It sounds like a minor technical detail,
Yeah.
but I'm guessing it's significant.
Real-time, or even faster than real-time simulation, dramatically speeds up the training process.
Okay.
Robots can experience many more scenarios
Yeah.
and learn from their mistakes much more quickly in a highly accelerated virtual environment.
Right.
Compared to the limitations of real-world interactions. They can essentially compress vast amounts of learning into shorter time frames.
Right.
Imagine trying to learn to drive a car
Yeah.
by only driving for 5 minutes a day
Right.
versus driving for hours in a simulator.
That makes perfect sense.
Yeah.
And they also mentioned that Newton integrates harmoniously into frameworks used by roboticists, like MoCo.
Yeah.
That seems crucial for adoption
It is.
within the existing robotics community.
Yeah.
It's not a completely isolated system that everyone needs to learn from scratch.
Exactly. Interoperability and ease of integration
Right.
are vital for any new technology.
Yeah.
To gain traction in a field like robotics, where various tools and platforms are already in use.
Right.
And they even showcased a demo with a robot named Blue
Right.
interacting in a simulated environment powered by Newton,
Yeah.
highlighting that real-time feedback and realistic physics.
Yeah.
That demo really brought it to life.
It did.
Seeing the robot respond so naturally to the simulated environment.
Now, there was one more significant announcement that caught my attention.
Okay.
The open sourcing of GR00T N1. I mean, that's a pretty big deal, isn't it?
It is a significant move.
What's the potential impact of that decision?
Open sourcing GR00T N1 has the potential to really accelerate innovation in the field
Okay.
by making the foundation model and potentially related tools more widely accessible.
Right.
They're essentially inviting the broader robotics community,
Yeah.
researchers, developers, and even hobbyists
Yeah.
to experiment, build upon, and contribute to its development.
Right.
It lowers the barrier to entry for many who might not have the resources to build such a sophisticated model from scratch.
So it could foster a much more collaborative and rapid pace of advancement
That's right.
than if it remained a proprietary technology.
Exactly.
We could see a proliferation of new applications and robot design emerge much faster.
Absolutely.
Stepping back and looking at the bigger picture here,
Right.
they mentioned that embodied AI and robotics could very well become the largest industry of all.
Yeah.
Given everything we've discussed, the advancements in data generation,
Right.
model architecture with GR00T N1,
Right.
and the scaling capabilities enabled by Newton.
Yeah.
That doesn't seem too far-fetched.
If we connect this to the bigger picture,
Right.
these advancements directly address those fundamental challenges we started with.
Yeah.
Efficiently generating the necessary data.
Right.
Developing sophisticated and adaptable AI models.
Right.
And creating the tools and frameworks needed to scale their development and deployment.
Yeah.
It's a holistic approach to building intelligent robots.
And it wasn't just about robotics either.
Right.
They also touched on Blackwell going into full production.
Yeah.
And the significant performance gains,
Right.
the growing importance of inference in AI,
Right.
and their annual roadmap for AI infrastructure across cloud enterprise and, of course, robots.
It all seems interconnected.
Yeah.
The advancements in the underlying computing power
Right.
are clearly driving what's possible in robotics.
So to summarize for you, our listener,
Right.
What are the key takeaways
Right.
from this deep dive into NVIDIA's robotics announcements?
Right.
We've seen how synthetic data generation with Omniverse and Cosmos is tackling the data bottleneck,
Right.
potentially revolutionizing how robots are trained.
Yeah.
We've explored the potential of the GR00T N1 foundation model as a generalist brain for humanoid robots capable of learning and adapting to a wide range of tasks.
Yeah.
We've delved into the advancements in physics simulation with the Newton engine,
Right.
which is crucial for realistic and accelerated training, allowing robots to learn more effectively in virtual environments.
Right.
And finally, the open sourcing of GR0DT N1
Right.
could be a real catalyst for innovation in the wider robotics community,
Yeah.
fostering collaboration and faster progress.
And if we connect this to the bigger picture,
Right.
these aren't isolated advancements.
Yeah.
They represent a concerted effort to build a comprehensive ecosystem
Right.
for developing and deploying embodied AI, addressing the fundamental challenges that have long held back the field of robotics.
Yeah.
It's about creating a future where robots can truly assist and augment human capabilities
Yeah.
in meaningful ways.
Absolutely. As these technologies mature and become more integrated,
Right.
we're likely to see a significant impact across various industries,
Yeah.
from manufacturing and logistics to healthcare, and even our everyday lives,
That's right.
as robots become more capable
Right.
and seamlessly integrated into our world.
This raises an important question for you to consider. With these rapid advancements in creating more capable and general-purpose robots,
Yeah.
what are some of the unexpected ways these technologies might reshape human work and interaction in the coming years?
Right.
Consider the implications beyond just filling labor shortages. How might our daily lives be different as these technologies become more prevalent?
Right.
It's a fascinating and rapidly evolving landscape to ponder.
It really is.
Yeah,
A lot to think about.
absolutely.
Thanks for joining us.
Yeah, it was fun.
We'll see you all next time.
See you next time.